Welcome. I'd like to take a look at an application example, culture growth. So we're going to create a relative growth rate model, but what we actually have is two pieces of information given that don't allow us to easily find the value of our growth rate. So again, growth rate model, relative growth rate model would have A of t is equal to some initial amount times e raised to the RT. I know that A of 1 is equal to 5,000, so P times e to the R is equal to 5,000. And I know that A of 4 is equal to P times e to the 4R, and that would be 8,000. So this gives me a system of equations. P times e to the R is equal to 5,000, and P times e to the 4R is equal to 8,000. I have a system of equations, but it's a nonlinear system of equations. Two equations, two unknowns. I should be able to find a solution for this. So what would it look like to solve this? Oof, man. Well, that's maybe a little bit annoying, but really not too bad. What I'm going to do is I am going to solve for P. Why? Because I can. Seems reasonable. I'm going to solve for P here. So we're going to use substitution. I can write P is equal to 5,000 times e to the negative R. So I divided by e to the R on both sides. Now I plug this into the second equation. That's going to give me 5,000 times e to the negative R times e to the 4R is equal to 8,000. I can divide both sides by 5,000 and combine these two terms here, right? E to the R times e to the 4R is e to the 3R. But I can also divide by 5,000 on both sides. So I get 8,000 divided by 5,000. So I get e to the 3R is equal to 8/5. Now I just need to rewrite in logarithmic form. So the natural log of 8/5 is equal to 3R. I can divide both sides by 3, so I get 1/3 of the natural log of 8/5 is equal to our growth rate. Excellent. Now I can use that growth rate to help me identify the initial population because, well, let's first write down what we have so far. A of t is equal to some initial amount times e to the 1/3 natural log of 8/5 times t. And I know that A of 1 is equal to that 5,000. So I'm going to be able to write this as P times E to the 1/3 natural log of 8/5 times 1 is equal to the 5,000. So P itself is equal to 5,000 times, right? I divide both sides by this or multiply by e to the negative of that. E to the negative 1/3 natural log of 8/5, which I can get an approximation for. Using our handy dandy calculator, we can find this to be 4,274.94. Of course, that's an approximation, and maybe we really want to round that to the nearest since it's bacteria. So 4,275. And we would finally say that our model should be A of t is equal to 4,275 times e to the 1/3 natural log of 8/5 times t. And that's what we were looking for.